A bird flies straight up at a constant rate of speed, 4 meters per second. We are standing on the ground 200 feet away. Our eyes are at ground level. Let's say we're laying there. How fast is the elevation angle theta changing 30 seconds after the bird takes off? This is a related rate problem. We'll follow the same outline we've been doing. Step one, we're going to outline the given information. The two quantities they gave us are both functions of time. The y is y of t, and the theta is theta of t. We should draw a picture of that. We'll be doing that. Here's the picture. Triangle, right triangle. Here's our eyeball on ground level, 200 feet away. So there's the angle theta, the angle of elevation, x equals 200. Z is the hypotenuse, y is the height. The bird's up there at the top. And the rate that they give us of change is the rate of change of the height, y. dy dt equals 4 meters per second. That's how the constant speed of the bird going straight up. Then we relate the theta and the y together by looking at the triangle. We see the tangent of theta is opposite over adjacent, it's y over 200. Now they want us to find the other rate of change. That's going to be theta dt when t is given to be 30 seconds. Step 2. Differentiate. Here's our solution. Okay, take the related equation tan theta equals y over 200 and take the derivative of that with respect to t. On the left, we use the sine squared theta and then hit it with the chain rule. D theta dt is equal to 1 over 200, that's a constant, times dy dt. And of course that's a chain rule here because see y, the derivative of y was just 1. Then we hit it with dy dt because y is a function of t. Solve for d theta dt alone. And when we do that we get d theta dt is equal to dy dx times 1 over secant squared, which is cosine squared theta over 200. So there you see we used a trig identity that says the secant is the same as the reciprocal 1 over cosine theta. Okay, that's where that came from. So there's our result of step 2. We're going to use that result and we're going to substitute the given information dy dt equals 4 and t equals 30. Okay, so the equation we're going to be using is the one here in the cloud. It has a y, no, it has a theta, it has a cosine theta in it. We're going to have to figure out what the cosine value is. So let's take that right triangle again. We'll draw it again down here. Here's our right triangle. There's the right angle. And theta is over here in the corner. We have x equals 200. We have y equals, okay, that's the height. It's rate times time. The rate that the bird was flying is 4, and the time that it's elapsed was given to be 30 seconds. So it's 120 seconds for y. And then, I'm sorry, meters or whatever these are, meters, feet. And then over here on the hypotenuse, we're going to use Pythagoras. Z equals the square root of 120 squared plus 200 squared using the two other legs. And that simplifies to 40 times the square root of 34. So we have all the sides to this right triangle. In a minute, we're going to use that to figure out what the cosine of theta is. Thus we have the d theta dt, this is a result of step 2, equals dy dx times cosine squared theta over 200. Okay, well that implies that d theta dt is equal to plug in the 4 for dy dx times, okay, what is the cosine of theta? I say it's 5. 5 squared for cosine squared. And of course the bottom would be the square root of 34, which is part squared because it's part of this cosine, times the 200. So why did I use 5 over the square root of 34 for the cosine of theta? Well, look at the picture. Cosine theta is adjacent over hypotenuse, so it's 200 over 40 times the square root of 34, which simplifies to 5 over the square root of 34. You square that, you get cosine squared. We plugged that in over here. That's where it came from. So d theta dt is equal to 4 times 25 over 34 times 200, which simplifies to 1 over 2 times 34 is 68. 1 over 68. Okay, that's I actually like that answer a lot. I would stop there, but just for reference purposes, that's approximately equal to 0.015, and the units are radians per second because it's a change in theta, the angle of elevation. The thing that was interesting is that we had to go through this right triangle deal just in order to get the value for cosine theta, which we had to plug in. We had to square it and plug it into the formula that we got at the end of step 2.